In this session, we'll generalize the delta function from one dimension to 3 dimensions. It's a pretty simple idea. You just take 3 delta functions, one for the x-axis, one for the y-axis, one for the z-axis, and just multiply them. You just form a product of these 3 delta functions, 3 bars by definition. So you define this D3, in a sense, 3-dimensional delta function at the position R. So at position R at coordinates x, y, z. So x, y, z. You define this as the product of these 3. Now, I'm not quite sure. You might be able to see the last line here of the previous session on the right here. So if not quite, I'll read it out. So delta x is 1 over 2 pi integral minus infinity to plus infinity exponential to the power I k x dk, right? So you do something similar for x, y, and z, and you end up with this definition. Okay? So since it's a simple product, so you get 2 pi all cubed, so 8 pi cubed. You get a triple integral because dx, dy, dz. And here you've k dot r, k the wave number vector, and r just your position vector. If you expand this out, it's a dot product, right? So you just get kxx plus kyy plus kz z, right? So this is just this. Okay. So here's an example of a 3-dimensional direct function. Okay. Double bar, double line, meaning new thought. We can now actually use. We can bring the delta function into quantum mechanics in a more intimate way now. So let these phi n's here, it's just not one function, it's a set of functions. So let these phi's, plural, here, be a basis set. Let them be orthonormal, right? So we've talked about this quite a bit. And complete in the sense there's enough of them such that any function, function of x, can be written as a weighted sum of these basis functions. Right? So I've talked about this before, but so like here's some arbitrary function psi, okay, and you can write that sort of like as in Fourier analysis. Right? So you can write that as a weighted, like these complex numbers, a weighted sum of these basis functions, orthonormal basis functions. And these coefficients here, again, very similar to the way you calculate them is the same way you calculate the coefficients, the Fourier coefficients in Fourier analysis. So these C's, they're just to calculate their value, you just form the bracket of your general function psi here with the corresponding orthonormal function phi of n. Now that by 3 bars, that's just the bracket, which is you remember from earlier lectures is defined in terms of the overlap integral here. So I put 3, but you've seen this many times before, so just revision. All right. So all that. Here that is revision, nothing new. But here something new that is interesting. All right. We now have this value here for the Cn. Now take this expression here, just an arbitrary, some general wave, some function that's a weighted sum of these orthonormal functions. Okay. Now here is your C, Right? Here it is here. So your Cn, these coefficients here, which is equal to this, the overlap integral if you like, or the bracket. Well, here doing it in terms of integrals. Okay, so you're just substituting this for the C in here, which gives you this. Now rearrange what's inside the integral a little bit. Take the integral sign outside. Take this to the right. No, just leave that to the right. So the integral goes outside. The sigma comes inside, and then you get the sum of phi n star x dashed x dashed. Right? But from the, I'm not sure. Can you? I don't know. See, I don't know if you can see this last. The bottom line of the left square of the previous session was an interesting result. The integral of f of x times the delta function x minus x bar, or x dashed, actually equals f of x dashed. So I don't think you can see that. Maybe just. But from this result, the starred equation, here it is. Oh, sorry, here it is. Yeah, I didn't need to. Yeah, so I've written it out again here. Okay, so the bottom line here is just this. Okay, and from this, you can see that this delta here is equal to this, the content here in the square brackets. Okay. So this here, this sigma of phi n star, x and x dashed, it is here, is equal to this, right? Because this is equal to that. Right? So this expression here, this sigma of phi n star, x and x dashed, is called a closure relation. Because closure, what does that mean? Depends on the mathematical context. Like in group theory, closure, that means you perform a binary operation on two elements of your set, of your group, and you get a result that's also in the set. So I guess in the same context, why is it called closure? Completeness and closure are closely related. This set here, this basis set, is closed in the sense, completely closed. Perhaps I should fluff that a bit. I need to refresh my memory. What's the difference between completeness and closure? Don't worry about it. Anyway, this expression here is called the closure relations. Right? Now, just finishing off, before we get into a whole new topic, I'll just say a little bit about the history of the delta function. For years, decades even, after Dirac, British quantum mechanic, invented the term, the concept, mathematicians hated it. They said, oh, this is a very poorly defined function. It's not mathematically rigorous, and they really didn't like it. And that went on for a long time. And then, as far as I know, in the 80s along came Ed Witten and revolutionized low-dimensional topology by using a quantum field theory approach. And then the mathematicians got very interested in quantum field theory because it helped them solve their problems in low-dimensional topology. Right? The topologists were fascinated by quantum field theory because Ed Witten found techniques that enabled him and the mathematicians, the topologists, to solve their problems far more easily. And so then you've got the topologists learning quantum field theory to help them with their topology. And an essential part of quantum field theory, of course, is quantum mechanics, and hence this delta function. And then once they became very familiar with quantum field theory and quantum mechanics, they realized the great value, the usefulness of the delta function. And so they said, oh, well, okay, as mathematicians, perhaps we should tidy this up a bit. And so the mathematicians found more rigorous definitions of the delta function, and hence they dropped their years-long, decades-long opposition to what they thought of as sloppy physicists' thinking, which is still pretty much a common value by mathematicians looking towards physicists. Okay, so now a new topic. The notion of compatibility and something called commutation relations. Now, the rest of this board, so this half of this session, and for at least 2 or more sessions, we will be talking about this because it's pretty important in quantum mechanics. So now we've from chapter 1, in fact, from the very beginning of the course, we introduced you one of the revolutions in quantum mechanics relative to classical mechanics was the idea of the Heisenberg uncertainty principle, right? The HUP, the HUP. And that is, if you remember, you cannot measure with infinite accuracy both the position and the momentum of a particle, right? When you try to measure the position very accurately, you disturb your particle so much that its momentum uncertainty increases, right? So there's kind of trade-off. Well, we'll be talking about that. Now, the position and the momentum are both observables, right? And they are incompatible, right? Rather like a couple go on their first date and say before computer dating, and one realizes the other is a smoker, and the first couple what's the word? Datee